define the term overvoltage. Increasing the value of voltage or its voltage level for a very short time in a power system is called overvoltage or the voltage surge. This voltage surge comes only for a few microseconds, but due to this, there is a much increase in a voltage level of the system. This may cause damage to the equipments connected in the network. Explain voltage transient with rise time, steepness and tail time. So a voltage surge transient wave is a sudden and temporary increase in the voltage that lasts for a very short duration, usually caused by switching surges or switching operations, lightning strikes or faults in electrical systems. It refers that the transient voltage surges are of duration of microseconds. The wavefront refers to the rising portion of the transient voltage wave like this. This is, you can see this blue line. It represents how fast the voltage increases from 0 to its peak value. The faster the voltage rises, the steeper the wavefront. This waveform is steep fronted, that means it reaches to its peak value in very short time. This time is known as T1, rise time. The value of this rise time T1 is approximately in the range of 1 to 5 microseconds. You can see this in this. The rise time is nearly 1.2 microseconds. Here it is written that wavefront is 1.2 microseconds. So it is 1.2 microsecond is the rise time. Steepness is the rate of change of voltage with respect to the time, that is dV by dt. That is, if we consider the voltage as 1000 kilovolt and rise time is 1.2 microseconds, then the steepness can be calculated like 1000 divided by 1.2. So it is 833.3 kilovolt per microsecond. This is how the voltage rises suddenly from 0 to its peak value. A higher steepness means a more abrupt rise in the voltage, which can cause a severe stress on the insulation. The steepness depends on the factors like source impedance, the propagation medium, and the load characteristics. A lightning impulse wave is often described as 1.2/50 microseconds, meaning 1.2 microsecond it is a rise time, that is the time taken to reach its peak value from 0, wave front time. 50 microseconds it is the time taken for the voltage to decay to its 50% of its peak value, that is wave tail time. It is referred as 50 microsecond in this. And steepness that I have already gone through is calculated by maximum voltage divided by its front time, that is TF, that is the rise time. So rate of voltage increase, so it is calculated with this. So here from the peak value to reaches its 50% of the value, this time is known as tail time, that is wave tail time. It is in 50 microseconds. This is the standard impulse transient voltage waveform. This is applied to check the equipment operation against the transient. Safeguarding and everything is checked by applying this magnitude voltage waveform, that is 1000 kilovolt, 1.2/50 microsecond rise time and fall time respectively. So this is about the voltage transient with rise time, its tail time and steepness. State the causes of overvoltage in power systems. There are two types of causes of overvoltage in power system. One is overvoltage due to internal causes and two, overvoltage due to external causes. These external causes are lightning surges only, whereas in case of internal causes, switching surge, arcing ground and resonance. Brief about overvoltage production due to the lightning stroke. So the lightning stroke is the external cause of overvoltage in power system through the sky. A lightning stroke is a natural electrical discharge that occurs between clouds or between a cloud and the ground due to the charge imbalance in the atmosphere. Inside a thundercloud, strong air currents cause collisions between ice particles and water droplets or particles. These collisions result in a charge separation. The upper part of the cloud becomes positively charged, whereas the lower part of the cloud becomes negatively charged. Thus, electric charges gets accumulated in the clouds due to the thunderstorms caused due to the atmospheric effect. The positive charges are accumulated in some clouds or some portion of the clouds, while negative charges are accumulated in some clouds. When this clouds passes over the ground, it induces the charge of the opposite polarity on the ground. The potential between the cloud and earth increases when there is the increase in the charge on the cloud. The charge buildup creates a strong electric field between the cloud and the ground or within the cloud itself. If the electric field strength exceeds the breakdown voltage of the air, it ionizes the atmospheric conditions around it, allowing a conductive path for discharge. This voltage becomes 5 to 20 million volts, or when the potential gradient becomes 5000 volt to 10,000 volts per centimeter. The potential gradient is not distributed evenly. It is more in the center of the cloud. Initial flash or streamer begins by the pilot ladder like this, the pilot ladder, yes, this, which conducts the accumulated charges. A steep ladder, a series of ionized air paths, extends downward the cloud from this top position of the cloud to this earth position. The pilot ladder continues to come down in small steps until the potential gradient of the tip is maintained by seeking the conductive path, means continuously it is ionized throughout the air from cloud to earth. When the pilot reaches the earth, there is increase in the electrostatic field of the earth, and the steamer going upward from the earth is produced, the return streamer, the return path from the earth to cloud. As a result, heavy spark is produced between the earth and the clouds. This is called lightning stroke. It is a rapid, high energy event that results from the movement and buildup of electric charges in thunderstorms. So this is how the overvoltage is produced through a lightning stroke. State different types of lightning strokes with figure. So there are two types of lightning stroke: A type stroke, or says upward leader stroke, and B type stroke, or say downward leader stroke. As you can see in the figure, the A type lightning stroke, in this a charged cloud is fall, or the lightning strikes on the tallest part or the tip of the tallest part of the building or skyscraper, or say high mast, high tower, or say windmill. There are the structure which is very high or above the ground. So at that time the lightning strikes occurs on the tip of this surface, is that surface is known as the A type stroke, or say upward leader stroke. Whereas in case of B type stroke, you can see this, the B type stroke falls on the earth's surface itself. So it is a B type lightning stroke which generally falls on the earth ground level. So at that time the stroke falls, or the lightning strikes occurs at the surface, is known as the B type stroke, or say downward leader stroke. Brief about A type lightning stroke. So it occurs when a leader from the ground, such as a tall structure or a mountain or the tip of the tallest structure, initiate the lightning discharge. The charges of opposite polarity are induced on the top of the tall buildings due to the charged clouds. This positive charge cloud is over the tallest building, and the negative, that is opposite polarity charge, induced on the top of the tip of the surface. The dielectric strength of that area is reduced, and a lightning results between the cloud and the building. It is commonly associated with all the type of tall objects like towers, skyscrapers, or wind turbines. It often involves positive cloud to ground lightning, that is cloud to ground lightning, which is more powerful and can last longer than the negative cloud to ground strikes. This type of lightning stroke is also known as A type of lightning stroke, which is also termed as upward leader stroke. So this is how A type lightning stroke occurs on the tallest part or the tip of the tallest part or the tallest structure of the earth. Brief about B type lightning stroke. So we have already seen two types of lightning stroke. One is direct lightning and another is the lightning stroke that is falling on the ground. First type A is the lightning stroke that is falling on the tip of the tallest object on the earth. So now we are dealing with the B type lightning stroke that falls on the ground itself. So a B type lightning stroke refers to a cloud to ground lightning discharge that is characterized by a high peak current, typically associated with the first peak or the first stroke in the negative lightning flash. Typical peak current is around 200 kiloamperes, which is significantly higher than that of the average lightning strike. Now suppose to understand this, consider there are three clouds A, B and C. Cloud A and C are positively charged while cloud B is negatively charged. Suppose these clouds are coming near to each other, then the cloud A is attracted towards cloud B. So in this case both the clouds are attracted and cloud C remains free. So the charges of the cloud C becomes free suddenly. So the lightning stroke is produced on any object or ground. In type B lightning stroke, it should be noted that it is not necessary that the lightning stroke occurs on the tall building. Current of 10 to 90 kiloampere flow due to this type of lightning stroke, and the period of this flash can be of 1 millionth part of a second, which is a very low period, and the voltage or the current magnitude is very high. So this is something or informative talk about the B type of light. Brief about lightning strike on transmission line. So there are two types of lightning stroke that we have already seen. A type lightning stroke that strikes on the tallest building or tallest structure on earth, or B type lightning stroke that generally falls on the ground. There is a possibility of both types of lightning stroke on the transmission line that falls or that strikes on the line. As a result, wave of very high voltage travels on the transmission line in two sides, both the sides. It burns the insulator and causes damage to the supports. The energy is dissipated through the inductance and resistance of the line when the direct stroke takes place away from the generating station or substation. The equipments may be damaged when the direct stroke takes place near the generating station or substation. So these are some detailing points or brief information regarding lightning strikes on transmission line. Explain static charging of transmission line due to the charge cloud. So the static charging of a transmission line occurs when a charge cloud passes over the line and induces a charge on the conductors without any direct lightning stroke. This happens due to the electrostatic field created by the cloud. So high voltage can also be produced in the line by traveling waves produced due to the static charges in addition to the direct stroke. Suppose there is a cloud with negative charges over the line as shown in the figure. This is the cloud having a negative charge. This is a transmission line running from one end to the other. So these are tower supports and this is transmission line. A sag is drawn. So as the charge is negatively cloud, it will induces the opposite polarity charge on the transmission line. So positive charges are induced on the transmission line that is bound with this cloud. So it gets neutral when they are connected or they are bound with each other like this, because the same amount of negative charge is in the cloud and the same amount of positive charge is in on the transmission line. Now this cloud will induces the charge without any direct contact. This is the static charge bound by this cloud because of it has a negative charge and the positive charge are induced on the line. Now suppose a strong wind blow that will shift this cloud, so this cloud will shift it. So now there is no cloud on the transmission line. So what about this positive charge? This positive charge are not now bound, they are free to travel in either direction. So they can travel on both the sides of a line, so they can travel on either direction of a transmission line like this. So this is termed as the traveling waves. The magnitude of this traveling wave is of 10 to 15 kilovolt and it has the steep wavefront like lightning strokes or the impulses. So this is how a static charging of a transmission line takes place due to the charged cloud passing on a transmission line. Explain internal causes of overvoltages in power system. So when there is sudden change in the circuit condition of the power system, oscillations are produced due to the inductance and capacitance of the circuits, and there is increase in the system voltage. This voltage is almost double the system voltage. Thus, the overvoltage due to the internal cause is very less than that produced due to the lightning strikes. It is not necessary to provide additional protection for the overvoltage caused due to these internal causes. If the insulation of the equipment or a line is designed properly, then equipment is protected against the overvoltages. The switching surges, resonance, arcing ground, etc. are internal causes of overvoltages in power system. Explain overvoltage due to switching on of the unloaded line. When the switching operation is done in the power system with or without load, the voltage produced as a result of this is called switching surge. An unloaded line is a transmission line that is energized but not connected to any load, means there is no current is flowing to the end users or devices. The line only has its own distributed inductance and capacitance. Overvoltage during switching on an unloaded line. So when this is done, the line behaves like a capacitor because there is no load to absorb the energy that is given to the line. The sudden application of voltage causes the line capacitance to charge rapidly. Due to this, transient overvoltages or oscillation occurs. This can be significantly higher than the normal line voltage and can reach 2 to 3 times the nominal voltage. This is often referred as energization transients or switching surge. Explain overvoltage due to switching off of the unloaded lines. So when an unloaded line is switched off, here's what happens. The inductance of the line tries to keep the current flowing even though the switch is open. This leads to a high voltage spike across the opening contacts of the breaker. The spike can cause arcing, prolonging of the disconnection and further worsening the overvoltage. The trapped energy in the line's inductance and capacitance can create oscillatory transients. Similar to the switching on of the unloaded lines, when the unloaded line is switched off, the voltage becomes double before becoming zero. Explain overvoltage due to switching on of the loaded lines. So overvoltage due to switching on of loaded line occurs when a power transmission line or distribution line is suddenly energized, that is switched on while it is connected to load. Transmission line have inherent inductance and capacitance. When switching on, the sudden connection creates a condition where the voltage and current do not initially stabilize. The line inductance resists sudden change in the current and line capacitance resists change in the voltage. This mismatch causes transient over voltages. Voltage is equals to 2 into Zn into I is produced, where Z is the natural impedance and Zn is equals to under root of L by C. So the value of this impedance depend on the line constants, not on the load. I is the instantaneous value of the current at the time of the opening of the contacts. Suppose natural impedance, that is Zn, is equals to 800 ohm of a transmission line, and circuit is switched off when current becomes maximum, whose value is 50 ampere suppose in RMS. Then the superimposed voltage will be 2 times Zn into I is equals to 2 into 800 into 50, that is RMS value, multiplied by root 2 is the maximum value. So it will give you 113.137 kilovolt. If the voltage of the line is Vm, that is maximum value of Vm, that is 132 kV, 66 kV or anything Vm kV, then the maximum voltage on the line will be Vm plus 113.137 kilovolt. So this is how the over voltage produced due to switching on of the loaded lines. Explain over voltage switching surge due to current chopping. So current chopping is a phenomenon that typically occurs during the interruption of low inductive currents such as magnetizing currents in transformer or no load currents in reactors. It's especially associated with circuit breakers, particularly air blast or vacuum circuit breakers, which can abruptly force the current to zero before the natural current zero of the AC cycle. This sudden interruption of current leads to sudden collapse of the magnetic energy stored in the inductance. Because the current is stopped abruptly, the collapsing magnetic field induces the high voltage surge across the contacts of the breakers. This is governed by the relation like V is equals to L di by dt, where di by dt becomes very large because the current is suddenly dropped to zero. This results in a high frequency transient over voltage, often referred as a switching surge or over voltage surge. These over voltages produced are removed by resistance switching or surge arrestor, lightning arrestor, etc. So this is how over voltages are produced due to current chopping. Explain over voltage switching surge due to auto reclosing of a circuit breaker. So auto reclosing is a protective feature in power system where circuit breakers automatically close after they have tripped due to transient fault for multiple number of times. That is open followed by close, open, close and then open. So this is how they are operating auto reclosing in auto reclosing manner, because to improve the reliability of a system. This is common in transmission and distribution systems where many faults are temporary and clear on their own in a short time. Now, when a circuit breaker recloses after a fault, if the fault is still persist or present, it trips again, means open again. This is safe and expected operation. If the fault has cleared but the system is not fully de-energized, then a surge can happen. Now understand it fully. When a line is de-energized by a breaker, that is opened up, it may retain a trapped charge, that is residual voltage, due to its capacitance. This trapped voltage can remain on the line of the contacts. When the breaker recloses again, there may be a voltage difference between the energized and the de-energized sections. If the breaker recloses out of phase with the trapped charges, it creates a high voltage condition. This is known as a switching surge. It is often of high frequency and can cause insulation damage or stress or even equipment failure. Value of the over voltage becomes high when the charged line is closed. In addition to this, over voltages are also produced due to interruption of current due to the fault
and short circuit, switching on of the magnetizing current, switching off capacitor, switching off HV reactor, etc. in the power system. So this is how the over voltage or switching surge produced due to auto reclosing of a circuit breaker.
Explain arcing ground in brief. So arcing ground is a phenomenon that occurs in an ungrounded or isolated neutral system when a phase to ground fault leads to repeated arc discharges. This occurs due to the capacitance of the systems, which allows intermittent current flow even without a solid current path or conductive path. Due to this, oscillations of 3 to 4 times the normal magnitude are produced. So these are some points or brief information regarding arcing ground. State the causes and effects of arcing grounds. So first of all, we discuss the causes of arcing ground. So as we have earlier discussed that it happens in ungrounded neutral system or isolated neutral system. So first of all, the causes of arcing ground is ungrounded neutral system. Second is system capacitance. Third is fault interruption and reignition. And last is voltage rise. These are several reasons or causes due to which arcing grounds occur. Now what are the effects of arcing grounds? So first of all, high voltage surges, equipment failure, system unreliability and electrical fire hazard. So these are several effects of arcing grounds. So if asked in the examination that write the causes and effects of arcing grounds, you can write like this. State remedies for arcing ground prevention. So arcing ground phenomena occurs only due to the floating neutrals or isolated system. So in this case, first of all, use neutral grounding method. Use of arc suppression coils or Peterson coils. Proper insulation maintenance and use of ground fault protection release. So these are some remedies for preventing of arcing ground phenomenon.
Explain over voltage is produced due to resonance phenomena. So over voltage is caused by resonance phenomena occur when inductive and capacitive elements in a power system interact in such a way that they produce abnormally high voltages at certain frequencies. These frequencies are termed as resonance frequency. This can lead to equipment insulation failure, power quality issues and system instability. When the inductive reactance of the line becomes equal to its capacitive reactance, the net impedance of the line becomes minimum or say equals to its value of resistance only. So the line behaves purely resistive. Series resonance occurs at this time. At the power frequency, there is no possibility of producing such kind of resonances in normal condition, as the value of inductive reactance and the capacitive reactance are not equal in the power at the power frequency time. But when XL and XC, that is inductive reactance and capacitive reactance, may equal at the fifth or multiple harmonic frequency and may result in the resonances. Over voltages are produced due to this type of resonance. At resonance, the energy exchange between inductor and capacitors can cause voltage magnitudes to rise significantly at specific points in the system. The current becomes very large, possibly leading to the voltage drop across the components. In parallel resonance, the voltage across the capacitor or inductor can exceed the supply voltage many times. Even with small currents, large voltages can develop across the components. In real power systems, this can happen due to switching operations, that is capacitor banks, line energization, load changes, faults and fault clearing times, harmonics, especially in case of nonlinear loads. This kind of resonance occurs, and due to this, over voltages are produced in the power system. So this is how over voltages are produced due to resonance phenomena. Explain effects of over voltage due to lightning stroke. The ill effect, that is adverse effect of lightning, happens in two ways: due to the direct stroke and due to the traveling wave. Overvoltage wave is produced and it travels rapidly on the two sides on the line when the lightning stroke comes on the conductor. It shatters the insulator and damages the poles. The insulation in cable, transformers and other devices can break down if the overvoltage exceeds its dielectric strength limits. This leads to short circuits, fires or permanent damage to the equipment. Sensitive electronic and power system components like relays, control systems and communication lines can be damaged or destroyed. Power transformers and circuit breakers may experience internal arcing and mechanical failure. Arc is produced due to this overvoltage between the two windings, and the normal voltage is itself is capable to maintain this arc. Oscillations are also produced, so the other equipments connected to the line may be damaged. High frequency components of lightning over voltages can interfere the nearby communication lines, leading to signal degradation or data loss. Even if the lightning stroke doesn't directly hit to the conductor, it can induce voltage in nearby lines via electromagnetic coupling between the cloud and the line. This can lead to false tripping, malfunction or communication signal corruption. Overvoltages can trip protective devices like fuse or breakers. This causes power outages, sometimes affecting large areas or critical infrastructure. So these are the effects of overvoltages due to lightning stroke. Explain effects of overvoltages produced except the lightning surge. So the voltage exceeds the dielectric strength of insulating material, or repeated surges like switching surges or high voltages stress the insulation, especially in capacitors, cables, transformers, motors, bushings and other equipments, leads to premature aging, insulation breakdown or even failure, short circuit or fire like. Surges can cause excessive current through components, results in overheating, melting or arcing across insulation or between two phases like or between conductors. Unwanted tripping leading to unnecessary power outages or process disruptions. Transformers and reactors may experience core saturation due to voltage spikes, increases magnetizing current, distorts waveforms and causes noise or overheating in transformer or reactors. Normally, the insulation of the equipment is designed such that it can bear these overvoltages. The insulation of the winding punctures if some of the voltages or increases too much, and it results in earth fault or face-to-face fault. Repeated overvoltages gradually degrade system health, higher failure rates, more maintenance and reduced overall system lifespan. So these are the effects of overvoltages produced except the lightning surges. State the methods of protection against lightning stroke. So the following types of protections are given against the lightning, such as protection against the direct lightning stroke, and another is protection against traveling wave. Now protection against direct lightning stroke is given by the following two ways. One is the earthing screen and second is ground wire. So these are the types or methods of protection against lightning stroke.
Explain need of earthing screen protection against lightning stroke. So when a lightning strikes a substation or overhead line, a massive current is introduced. The earthing screen provides a low resistance path to ground, safely directing the lightning current away from sensitive equipment. Lightning induces overvoltages in electrical systems, and earthing screen helps dissipate the energy over a wider area and reduces the severity of surges.
A lightning strike also creates strong electromagnetic fields, and an earthing screen acts like a Faraday cage, shielding the equipment from electromagnetic interference. It minimizes the step and touch potentials, ensuring the safety of maintenance personnel by preventing dangerous voltage differences across the ground during a lightning strike. It reduces the chances of flashovers, insulation failure, or outages in a way enhances the reliability and longevity of the power systems. So these are some points that need of earthing screen protection against lightning stroke. State the advantages of earthing screen protection against lightning. So it provides a low resistance path to ground, safely dissipating lightning currents. It helps to minimize high voltage transient induced by lightning strikes, protecting insulation and equipment. It acts as a Faraday cage, protecting control and communication circuits from electromagnetic interference. It reduces outages and downtime due to lightning related faults. It reduces step and touch potentials or voltages during a lightning strike, ensuring personal safety. It has no active components, so it operates continuously without need for manual interventions. So these are some advantages of earthing screen protection against lightning strikes. State the limitation of earthing screen protection against lightning. So there are several limitations of this type of protection, that it cannot completely eliminate the effects of very high energy lightning strikes. Initial setup, especially for large substations, can be expensive due to material and labor. Over time, corrosion and ground resistance changes can reduce effectiveness, requiring regular inspections and maintenance. It provides protections mainly within its physical coverage area, that is in the substation only. It doesn't protect long transmission lines. Proper installation needs a wide area to spread the earthing mesh and ensure effective grounding. The effectiveness is heavily influenced by the soil resistivity. High resistivity soil reduces its performance. Coordination needed with other systems, as it often used along with surge arresters, shielding wires and grounding rods for full protection against lightning. So these are several limitations of earthing screen protection against lightning. Explain ground wire protection against lightning stroke. So ground wires are strategically placed above or alongside the structure or equipment to be protected, usually at a higher elevation than the protected objects. Overhead ground wire helps to protect transmission line against lightning strike. Hence, on a transmission line tower, similar like conductors, one or two ground wire run above the line conductors. The ground wire along with the grounding system provides a low resistance path for the lightning current to flow into the earth. When a lightning strike hits the ground wire, the electrical current is safely conducted to ground through the grounding systems along with the ground wire, preventing it from damaging the protected structure or equipment. So this is how the function of ground wire protection against lightning stroke. State the advantages with ground wire protection against lightning. So the ground wire intercepts lightning strikes, preventing direct hits to the phase conductors, reduces power outages and equipment damage. By safely directing lightning induced surges to the ground, it helps maintain the system stability and prevents insulation breakdown. So it provides a low resistance path for the fault currents, ensuring rapid fault clearance. It reduces the risk of electrical shocks to the maintenance personnel and nearby infrastructure by properly grounding stray currents. The line conductor gets electrostatic shielding due to the ground wire. So due to this, the induced voltage in the conductor by the discharge of the clouds are reduced. So these are several advantages. There are so many other advantages with the ground wire, but these are helpful to write in the examination if asked. State the limitations with ground wire protection against lightning. So there are several limitations which are addressed with ground wire protection, but some of are listed over here, like ground wires in case of extremely high energy lightning strikes can still cause flashovers to phase conductors, leading to faults. So they are not appropriate one. Improper shielding angles may leave portions of the line exposed to the direct strikes. So they may cause the improper protection of system against lightning. It may induce high voltages in adjacent phase conductors during the fault condition, leading to insulation stress and potential equipment damage. Ground wire installation requires additional materials, structures, and periodic maintenance, adding to overall cost of the transmission system. They do not significantly reduce the risk of power frequency faults, as they are designed to protect against the high frequency lightning strikes. Repeated exposures to the lightning strikes, strong winds, and ice loads can lead to mechanical damage, reducing its effectiveness, and they may cause the ground wire failure or the breakage of the ground wire. This may cause the protection failure against the lightning. Less effective against switching surges caused by circuit breakers operations, like making and breaking of switching circuit breaker causes switching surges. So protection with the ground wire is not appropriate or effective against those surges. So these are some limitations with ground wire protections against lightning. State the points to be taken care with ground wire protection against lightning. So the following points should be kept in mind so that good protection is achieved against lightning. So footing resistance of a tower should be as low as possible so that the ground wire can work effectively and easily ground the lightning strike. Ground wire should be of non-corrosive material. Sufficient clearance must be maintained between the line conductor and tower and line conductor and earth. There should be sufficient clearance between the ground wire which is on the top of the tower and line conductor. The angle of protection should not be more than 30 degrees. So these are several points to be taken care or kept in mind while ground wire protection against the lightning strike. Explain the term protection angle with reference to earth wire. The angle between the vertical plane passing through earth wire, that is this line, and through the ground wire, this, and the plane formed by the outer conductor and earth wire, this angle, this line and this angle between this is called the angle of protection. This angle of protection should not be greater than 30 degrees. Need of lightning arrestor or surge diverter against traveling wave protection. So first of all, traveling waves are high frequency surges that propagate along the power transmission lines due to sudden disturbances such as lightning strike or switching surges. Sensitive components like relays, capacitors and electronic devices can be permanently damaged. High voltage surges can break down insulation in transformers, circuit breakers and any other equipment associated with. High voltages can cause air breakdown, leading to arcing, and repeated surges can lead to power system disruptions, outages and system failures. Resonance occurs due to the steep wavefront and high frequency oscillations are produced in the electrical equipments or apparatuses. Due to these reasons, it is necessary to give protection against the traveling wave by the lightning arrestor or the surge diverter. Explain operation of lightning arrestor against traveling wave protection. So, by making the use of earthing screen and earth wire, protection against direct lightning stroke is obtained and voltage is induced due to Electromagnetic or electrostatic effects are sufficiently reduced, but no protection is obtained against traveling waves. The device used for this is called lightning arrestor or the surge diverter. Lightning arrestor is kept at the suitable place in the substation. It is connected between the line and earth. You can see in the figure as well. It is connected between line and earth. A gap is in between. This is a lightning arrestor. In normal condition, the air gap is sufficient for the line voltage, so the current does not flow to the earth because it is open circuited. See this? This is open circuited through the diverter. But when the traveling wave comes on the line at the diverter and reaches to some voltage, this point P, this value, the breakdown of air gap occurs and the arc is produced. So the diverter gives low impedance path, so the additional charges on the line are grounded with this here. This is conducting, so the current is passing through this line to earth. It should be remembered that the surge diverter should give low impedance path only when the traveling wave comes and not before or after. So this is how lightning arrestor is used to protect the equipment against the traveling waves. State the essential characteristics of surge diverters. So there are several characteristics of surge diverters. The following are essential or needful characteristics for good surge diverters, like no current should flow through the surge diverter in the normal healthy condition. Easy path to earth should be given by the diverter when the overvoltage comes. The diverter should be capable of withstanding discharge for some period of time after the discharging of current itself. The secondary transient should not be produced during this operation. The surge diverter should work normally as before after the transient is suppressed. Means once the transient part is over or suppressed, the surge diverter should work normally as before. If the impulse ratio is unity, it means the arrestor will be able to divert the wave of any time duration. This is the essential characteristics. So these are some essential characteristics of surge diverters that we have discussed.